Hello and welcome back. So today we will start with linear regression, and I'll give you a brief idea of how the concept of linear regression or how linear regression works in the first part of this second session. And the second part will be, as usual, we will do hands-on on linear regression, and we will also try to dive deeper into Python through this hands-on now. Okay. So first we will learn how to do univariate linear regression. So what is univariate? From the name you can understand, we will try to predict something from only one variable. Okay. So let's see an example. Let's see these are marks of students maybe in an university, and based on the marks we are trying to predict the salary. So we have the marks and salary of a range of students. Say this is marks in some final exam. If it's 800, maybe out of 1000, the salary is 20,000. If it's some student who got 850, got a salary of 27,000. Okay, and we are trying to predict if you get a marks of 840, which is not there in the data, what salary would you get? Okay. So let us plot this data with x as marks and y as salary. So we have only one variable based on which we are predicting, that is marks. Okay, and if we plot the data, this is how we see the marks against salary. And if you see, we could try to draw a line which passes through all these points. And while trying to do that, if we find a reasonable line which almost covers close to each of the points, and we take the 840 and project it on that line, we get somewhere here salary around a little less than 25,000. Okay. Now it turns out that okay, so we know that the formula of a line is y equal to mx plus c, where m is the slope and c is the intercept. So this is not 0, 0. It starts from 18,000 here. So c would be the intercept of where it passes through the y-axis. Okay. So using this, assuming that the points are close to a linear a line which follows this formula y equal to mx, a straight line formula, we could get a formula for calculating m and c from these data points, and I'll explain you how we derive this formula. So using that formula we get, you can see we have got the value of c. So we get the value of m first, and from m we actually get c. Please ignore, I mean, we don't get c first. We will get the value of m, and from m we can derive the value of c using this second formula. Okay, and based on that, if we fit in m and c and have our x, then we get that the salary would be around 24,839, which is pretty close to what we saw graphically. Okay, so how we did that? So we made two assumptions. We assumed that if this line, this is the error, like suppose if a student gets 780, and we formulate and try to predict the student's score using this line, we would predict somewhere around 20,000, right? But the 780 student actually got 18,500. So that is the error at this point. And if we take the square of all the errors, okay, and plot them, it would since it's a square, it would form some sort of a parabola, and we would try to find the point on the parabola which is minimum. So the point that is the slope on this equation would be 0. It's parallel, it has no slope, this line. So how we find the slope of this equation? We have to do a differentiation over this. Okay, so we take the differentiation and equate it to 0 to get a few equations. And another assumption we make is the mean of the difference of these errors from this line. If we take the mean of all the errors, the mean should be 0. Using these two formula, we derive this m and c using these two assumptions, and we get the formula. Okay, and of course we have assumed that it's linear. Okay. Now we move to multivariate regression. Okay, before that, few interesting facts. If you see this formula, you can see it's a rearrangement of this formula, which is correlation of xy into standard deviation of y divided by standard deviation of x. And you can also find by this method how good our prediction will be. That depends on the correlation of xy square, which is also known as the r square. Okay, and there are few other formulas which helps us to check the confidence of this prediction of M and C. Okay, I'm not putting those formulas here, but if required we can explore them later. Okay, and then we have multivariate regression. Here let's see the data now. Previously there was only a single variable, but now we are trying to predict the marks or the salary based on marks of 3 subjects, maybe in the final semester out of 100. Okay, so each student, and we have marks of each student in 3 subjects. So so these are multiple variables trying to predict salary, multivariate regression. Okay, so that's where matrix x values, they would actually create a matrix here, right? It's a matrix. It has 6 rows and 3 columns. So a 6 cross 3 matrix, and we will learn whatever is required or whatever basics of matrix are required. We will learn along the course. Okay, we will not have a separate session on matrix. Okay, and now let's see y. Okay, the y is a vector. Okay, a list of variables. Okay, so let's assume that some weights are there along with this x, like w1 into 85, w2 into 80, and w3 into 87 would give 20,000, and the same w1 into 90, w2 into 88, and w3 into 92 would give 27,000. Right? It's the same linear equation again, but in a high dimensional space. So we need 3 w's here. Okay, but how do we find now we have to find, if we find these w's, we can predict the weight, we can predict the salary given the 3 marks of any student, right? And again there will be some prediction error. Our goal will be so that we have the least amount of deviation on our predicted values, which we can find out here. Like once we find the weights which moderately fit all, what is the difference when we predict with these values of y. So so the formula comes like this: wixi plus w0, which is the intercept in a high dimensional place. So let's assume this w0 as w0 into 1, and let's assume we have one more variable which has value 1 in all the fields. So our matrix is now changed to this. It has 1 all along, and this continues, and so the equation is generalized as wx now. And it turns out that using matrix algebra we could solve this equation and get w like this. Here xt means x transpose. The transpose of a matrix is just rotating the matrix so that the rows become the column and column becomes the rows. So x transpose x is the product of the matrix with its transpose, and then we take an inverse of a matrix. What is inverse of a matrix? The inverse of a matrix when multiplied by that matrix gives the identity matrix, and then again we multiply with x transpose and then with the y vector. Okay, using this this is how the calculation would look like. This is the transposed matrix. If you see, the rows have become columns and columns have become rows, and this is the original matrix. You have the product, then you can find the inverse. There's a complex formula for finding the inverse, and it complicates as the dimension of the matrix increases, or the columns or the rows of the matrix increases, and then and we can find inverse only of a square matrix. So when we do x transpose x, the product becomes a square matrix, that is same number of rows and columns, and then again we multiply by x transpose, and finally we multiply with the y vector. Actually it will be a column vector over here. And see in the next page, so we get this weights. Now, so these are the weights. The W, this is W1, W2, W3, and this is the W0 for the 1. You remember we had put a column of 1s. Okay, so now if you are provided with a student who has got COA, computer organization architecture 85, data structure 85, and object oriented programming 85, and you have to predict the salary, so you would take these weights and multiply with the marks and put a 1 for the interceptor, which we going forward will term as the bias term. Okay, and here you get the predicted salary. So now you are into the domain of predictive statistics or predictive analytics. So we can predict the marks with these weights. Please note again, we can predict the salary. Please note that again there is an equation through which we can find the confidence intervals of this prediction. Okay, and some drawbacks of this approach. So x transpose x, we take the inverse, if you remember in the previous slide, and it might not be invertible always. And second is when we have large amount of data, then finding x transpose x becomes finding the inverse of x transpose x. It's a huge calculation even with the system, and it might fail, it might not be feasible. So we will go to an alternate technique of regression, right? So we'll do it with gradient descent, which is one of the optimization techniques. Okay, so here you remember our x matrix, and we have our y vectors. So, and we want to find some weights W0, W1, W2, W3. So now we will find these weights using an iterative approach in optimization. It's a very interesting approach. Now see, we will randomly assign the weights first, anything. So in this example we are taking the weights as 0, and we will make a prediction of y with all the x values we have. And by putting zeros, of course all values will become zeros, and it will not be anywhere near these points. Okay, so we can find the difference of what was our prediction error with this random weights. You can also take any random values. So, and we take the square and half it, so that you will realize this is for a mathematical purpose, this has been taken as half. And with this what we do, we find an error, squared error, mean squared error. So we divide it by the number of observations. It turns out that if you try different weights, a combination of random weights, since it's a square, you would get something, a curve again like this parabola. Okay, this is a hand-drawn parabola, so the shape is not that good. Okay, and maybe with these weights you are somewhere here, or maybe here, or maybe here, and we want to find the weights which would bring us somewhere here, right? That is the lowest error. Okay, so how do we do that? We have to find the slope at this point. Okay, and decide whether we need to move left or whether we need to move right, where we are in this point. Okay, and we need to descend to this point. If we are here, we need to descend over here. So which direction we need to go, we can find out from the slope at this point. And how do we find the slope? We do take the derivative of this equation, this E, at this point. Okay, here we take the derivative. Okay, so now this derivative value helps us decide whether the next variables, we won't take it randomly. It's a huge number of random variables, we cannot try everything. So we can decide after the first random set which direction. So we would adjust our weights using these derivative. So every weight is subtracted with alpha times this derivative value. Why alpha? This is the learning rate, how much we will move in any direction. Okay, and say we move and we get the slope comes over here, and then the slope moves further down, and finally like this after few iterations, sorry, this went away. Finally, after few iterations, we get this final point where the error is lowest. So we get the final set of W's at this point, and those are the weights we can use for prediction. So you can note here that we are actually considering that the relation is linear, and but we can also predict this for polynomial regression. I mean, if the relation with y was not linear, okay, so it was not a straight curve, or it was some sort of a curvature line. Okay, so how do we do that? For polynomial regression, we have to raise these variables to some power of x. Like say we had two variables x and y, and we want to raise it to the power of 2. It would be x squared plus 2xy plus y squared. So we have to prepare variables which are square of this, and 2 into the product of this, and then use those to do a regression on gradient descent, and that would give us weights for a polynomial regression. Okay, however, so we come to the end of this session here, and we conclude the regression here. There are several things, other things also in regression, like confidence intervals, and we can go to more complex concepts like regularization, which would help us to, and biases and variances. As we go along, we will learn those concepts also, and next we will do some hands-on regression where we will try to dive deeper into the Python related concepts. Okay.